Hi class, this video is on topic D6, single slit diffraction and diffraction gratings. And this provides a high-level view of both of these topics. So if there's a hole in a barrier and you shine a light through it, just a single hole, based on grade 10 science, you might think that there's a hole-shaped beam of light that you'd see on a screen placed a certain distance away. And this is certainly what you'd see overall for a big hole with an everyday light source like a flashlight. However, in grade 12, we know a lot more about light now, and you might guess that the answer is not so simple. So under certain conditions, we get a diffraction pattern from a single hole that consists of a bright central region surrounded by alternating light and dark bands called maxima and minima. And this observation is called single slit diffraction or single slit interference. And since we've recently finished Young's double slit interference, you might see some similarities between this single slit diffraction pattern and the double slit interference. But at first, when you see single slit interference, you might wonder how can there be interference if there is only one slit? So recall that Huygens principle says that each point along a wavefront acts as a point source for a new spherical wavelet. And some of those wavelets will be blocked by the barrier, and some of those wavelets will go through the hole. And if the hole is small enough, the limited number of wavelengths that go through will interact, causing diffraction. Oh, I said wavelet, not piglet. And ultimately, these are regions of constructive and destructive interference. So I said under certain conditions, we get that diffraction pattern from a single slit. So these are the conditions. We have the width is narrow enough that a substantial amount of diffraction happens, but not so narrow that it acts as a single point source of waves. So if you remember, there's criteria for diffraction when you compare the wavelength and the width, W and lambda. So that comes into play here. And so for number one, for example, if the slit width was 100 microns, that would be considered a slit where there's substantial diffraction, but not just a single point source of waves. For number two, the second condition is that the light source is monochromatic. So for example, we have a red laser light, which is a wavelength of like 650 nanometers. And the third condition is that the light source is far from the slit so that the light rays that reach the slit are traveling approximately parallel to each other. And assume that these three conditions are all met whenever we have a problem in this course that says single slit diffraction. So those are assumptions that are valid in this course for single slit diffraction. Fraunhofer diffraction is a special case of diffraction that shows distinctive differences between the bright central fringe and the darker flanking fringes. And one example of this is light traveling through a narrow single slit. So if the opening is circular, so this is like a cross-sectional area of that barrier, and here would be your light source. So here's the barrier, and if this was circular hole, then the diffraction pattern that you would get is a pattern of concentric circles. And this is all just like looking just along one dimension of this. If, however, instead of a circular hole, if that opening is a vertical slit like this, then we'll get vertical bands of light and dark. And light through a narrow opening like 100 micrometers, or they're also known as microns. So that's that Greek symbol mu with M. So 100 microns produces a Fraunhofer diffraction, which shows a central bright fringe, which is called a central maximum, and it's bordered by dark fringes, minima, and less intense, brighter fringes, the secondary maxima. So once again, the central maximum is the bright central region of the interference pattern here and here. And then the secondary maxima are the progressively less intense bright areas outside of the central region. So each one of these little bright flashes of light, those would be secondary secondary maximum. So the bright spots are all maxima. So the bright spots are all maxima. The middle one is called the central maximum, and then all the other ones are called secondary maxima. Then you also have every dark spot is a minimum, and there's the first order minimum, second order minimum, and so on. If you take a look at the intensity, the central maximum is much more intense in terms of amount of light, intensity of light. And we can explain the observed areas of constructive and destructive wave interference by thinking of Huygens wavelets as wave sources. And these waves, so here's one wavelet, the path of one wavelet, or the wave ray associated with one wavelet, and here's the wave ray which is associated with another wavelet, and recall that the wave ray is 90 degrees to the wave front. And if we take a look at the path length difference between two wavelengths, the path length difference might be just enough for destructive interference or just enough for constructive interference. And based on the path length differences, if those path length differences are all multiples of a half a wavelength, then you get destructive interference just like before. And just like we did for the double slit interference, and then whole multiples of a wavelength would be constructive interference for path length difference. And then based on that, we can derive, based on this diagram, which is similar to what we've seen with the double slit, we can derive equations for the dark fringes and the bright fringes. So we have W, which is the slit width, sine theta equals n lambda. The n corresponds to the minima number. So the first order minima, we'd sub in 1. We'd sub in 1 here. So these are for the dark fringes. We're using letter N. And this actually does seem similar, but it is important that you notice that how this is going to vary from the double slit. So W versus D. So W is slit width, whereas D was the distance between those two slits. And then we also, similarly, can derive an equation for the bright fringes. So the bright fringes or maxima result from constructive interference and occur at angles of theta m that satisfy W sine theta m equals m plus a half lambda. And the order number of the maxima is indicated by m, and it's whole numbers. So once again, you have to know how the bright fringe equation varies from the dark fringe equations, not by memorizing, but just identifying that they're different. This piece over here, because of the fractions of a wavelength. So the dark fringes come from half a wavelength intervals. And you might wonder, well, then why do you see the 1/2 in this equation? It comes from the derivation. So you get a point where you get theta over 2 and W over 2 because of the math of the triangle that is formed here. So yeah, you can look up the equations. You don't have to memorize them, but it's based on the path length differences and that little triangle. And then the distance between fringes, we have an equation for that. So the distance between successive minima or successive maxima is given by lambda L divided by W. And the width of the central maximum is 2 delta Y. So we could find that value, and then if we needed, that would be for maxima to maxima, unless you're talking about the width of the central maximums, or minimum to minimum. If it's sandwiching the central maximum, then you'd have to do double that. So delta Y is that distance, lambda is the wavelength in meters, length is the distance to the screen in meters, and W is the slit width in meters. So make sure you have SI units. As you've seen in this unit, you have, and other units in this course, it's often you have orders of magnitude bigger or smaller than your SI meters. So make sure you know, let's say if it was light, you've probably got nanometers to sub in here, and width, it might be microns. So micrometers, micro means 1,000,000 times smaller, and then nano means 10 to the 9 times smaller. So make sure you do times 10 to the minus 9, times 10 to the minus 6, and do your unit analysis. There is a really great Khan Academy video that shows sort of a color-coded animated explanation for the derivation of these equations, and I do recommend that at the end of this video. So this figure shows the intensity across the width of the diffraction pattern, and for each successive bright fringe, there is more of this slit acts as point sources of light, and then that will interfere destructively. So that explains why there's such a difference. The intensity of the bright fringes decreases away from the central peak. Okay, let's try an example. Light with a wavelength of 670 nanometers passes through a slit with a width of 12 times 10 to the minus 6 meters. This could have been 12 micrometers. Could have been written like that. The screen is 0.3 meters away. How wide is the central maximum? So we have our wavelength, we have our slit width, and we have the distance to the screen. So we have everything we need to calculate delta Y. And then if we're talking about how wide is the central maximum, we've subbed in everything in SI units. We calculate that delta Y, and then we're going to multiply it by 2 to get the width of the central maximum. Okay, let's try another example. If the first nodal line in a single slit diffraction occurs at an angle of 15 degrees for light with a wavelength of 580 nanometers, what is the width of the slit? So we're solving for W this time. So the first word that gives you a given, or the first piece of given, is that it says the first nodal line. So we know n equals 1, and it says first nodal line. So the fact that it's a nodal line, it's indicating destructive interference. So we know it's an n and not an m. And first means that number is 1. So n equals 1. And it's a single slit diffraction, so we can assume those 3 conditions apply. Angle is 15 degrees, so theta 1 is 15 degrees. We have lambda 580 times 10 to the minus 9 meters. What is W? So we just write our formula, rearrange for the thing we're solving for, and we get 2.2 times 10 to the minus 6 meters. You could also write this as 2.2 micrometers, or 2.2 microns. Okay, so the last part of this lesson is about something called a diffraction grating, which actually would look like this. So it's difficult to measure wavelength of light accurately using the interference patterns from double slit or single slit. And it's a lot easier if we can use a diffraction grating. So the problem with the double slit or the single slit is that the pattern might be dull or the resolution is fuzzy. So to solve this problem, most researchers use a diffraction grating instead. And a diffraction grating is a device with a large number of equally spaced parallel slits that produce interference patterns. So you can see there's a bunch of slits cut into this barrier. So this is a picture. And the diffraction grating produces interference patterns that are similar to the double slit. So this is what intensity over the width of the screen would look like if it was just a double slit. And now if we increase to 3 slits, this is what we would get: 10 slits, 100 slits. So the maxima are not as narrow as they could be, and as intense as they could be. So determining the wavelength from a diffraction grating is a much more accurate method, because if we want to take measurements between along here, which would be the angle or the width of the screen. So if this is your light source, that would be like a 10-degree angle away from the central line. So yeah, we can get that angle much more, it's a much sharper measurement. Zero order maximum is the location of the maximum intensity in the diffraction pattern. All wavelengths arrive in phase. Zero order maximum, we've got the first maximum of intensity on either side of a zero order maximum in an interference pattern from a diffraction grating. So here we have the zero order maximum, and then we have first order maximum and first order maximum on the other side. Theta 1 is the angle of the first order maximum, and it's where the path length difference between successive slits is lambda. So whole number multiples of lambda. And do you recognize that diagram? Because we've done that diagram a couple of times before. We're looking at the path length difference. So we can use that path length difference and what we know about constructive and destructive interference to calculate, to derive an equation. So the path length difference for constructive interference has to be whole number ratio, whole number multiples of the wavelength. Oops. Whole number multiples of the wavelength. So our path length difference has to be 2 times lambda, 3 times lambda, 4 times lambda. And the path length difference based on the diagram is W sine theta n. So we can put those together similarly to what we've done for the double slit or the single slit, and we get m lambda equals W sine theta. And that's the angle. We're talking about the angle compared to the central line, slit width, and it's the mth order maximum. And that angle would be specific for that mth order maximum times lambda. So I'm gonna do one example to show you how that works. But first, just let's look at changing the number. So the number of slits. So at angles between maxima, the light interferes destructively, resulting in a wide dark band and narrow bright bands with a diffraction grating. And as the number of slits increase, the width of the maximum increases. So again, this diagram, as the number of slits increases, the maximum becomes narrower. So finding that angle would be easier, cleaner. Since a typical diffraction grating has thousands of slits, the maxima it produces, are in precisely defined directions. And also when the separation between the slits is small, the maxima are widely separated from each other. Okay, our last example. We've got a 1 centimeter diffraction grating producing a third order bright fringe at 22 degrees from the center for red light with a wavelength of 694.3 nanometers. Calculate the number of lines per centimeter on the grating. So we don't specifically have an equation for the number of lines per centimeter, but it's a 1 centimeter diffraction grating. So if we can find the number of lines, then that is our answer for the number per 1 centimeter. So we've got m lambda equals w sine theta, and we are solving for w. W gives us our slit width. So if 1 is, sorry, I think I just said W was slit width, but okay, W is slit spacing. So when we solve for W, we're solving that it's this many so if we have this slit spacing, it's this amount of meters from one line to the next. So 5.56 times 10 to the minus 6 meters per line of space per line. Then we can use that ratio with the 1 centimeter that we know the diffraction grating is 1 centimeter. So I would actually prefer to do this using unit analysis. I would say 1 centimeter times, and then I would use this as a ratio, but I would flip it. So it would be 1 line divided by 5.56 times 10 to the minus 6 meters. That's how you get the division. I mean, you don't have to do unit analysis for something that maybe is intuitive, but for me, I think it is easier for me to say, well, I've got 1 centimeter, and I know it's in total, 1 centimeter in total, and it's this spacing between the lines. So if we want to know how many lines, we would do the total width times 1 line divided by this distance. My mouse is running out of batteries. And so our final answer is 1,800 lines. That is 1,800 lines in that 1 centimeter. So yeah, just going back, I think I might have said slit width, but again, W is slit spacing. And I think that is the last example. So these are practice questions that I would recommend doing for reinforcing these 2 concepts. There is an exit ticket for this lesson, so please submit it. And I hope you have a great day. Stay safe.